Welcome to a new year in chemistry. Chemistry to me is one of my most favorite classes because I enjoy the way it works. It sort of lends itself to my logical mind and how things are put together. And as you study chemistry, you'll realize that this chemistry opens a great amount of opportunity to someone who wants to go further in the study of chemistry. You'll notice in this slide that chemistry is central to many primary sorts of endeavors, including nuclear chemistry, chemical physics, chemical engineering, which is the major that I was in, but is also extremely important in areas outside of what would be obviously related to chemistry, such as food science, agriculture, medicine, and toxicology. And there is something known as the STEM sciences. And the STEM sciences, STEM stands for science, technology, engineering, and mathematical. And those are areas of study that are being emphasized, particularly some years ago, a governor or a mayor candidate in Lexington was going to offer free tuition to people who would take STEM science type courses and promised to stay in the area for a period of time. Unfortunately, he didn't win the mayor election, so he didn't end up being able to implement this, but it was a really nice way of trying to promote this sort of study. I will tell you that this area of study is an area which has a lot of opportunities in terms of financial support. First of all, you probably remember this from basic science, and I actually intend on speaking about this in the basic science class. And this is the foundation of the scientific method. And the scientific method starts out with an observation, and this observation has to be coupled with a curiosity or some degree of inventiveness, something that makes you want to know why the observation has occurred. And at this point, the scientific method forms a hypothesis, or in other words, makes a prediction about what the observation is going to, or what is the reason of the observation. Then the person will develop an experimental design to prove or disprove the hypothesis. And during this experiment, they'll make more observations. Now, if the results do not confirm the predicted hypothesis, then another hypothesis has to be taken into account. If, on the other hand, the experiment does seem to be consistent with the predicted hypothesis, this begins to develop what we call a body of knowledge. Now, the body of knowledge, people continue to question that body of knowledge, and foundational to science is the idea of being somewhat skeptical of any particular understanding. In other words, it's not scientific, if you will, to accept anything as fact simply because somebody tells you it is. And so if you continue to be skeptical of this, two things can happen. One is that the additional testing will support the body of knowledge, or it will not support the body of knowledge, in which case the paradigm will have to go back and you'll have to start thinking about this again. On the other hand, if it supports to some extent, it's generally the hypothesis becomes what's known as a scientific theory. If, on the other hand, there is a great deal of additional testing supports the observation, it can become what's known as a scientific law. Now, the difference between a theory and a law is really somewhat hypothetical, although it is felt that laws, such as the law of gravity, is much more well established than theories, such as the theory of relativity. Although both are felt to be true, and it's important not to make a big deal about something being a law versus a theory. I know a lot of people talk about the theory of evolution and they discount it because it's called a theory. Now that would be a mistake. It has a lot of evidence to support it, and many scientists support it. And so it's important not to emphasize this word as a way of discounting its validity. Now, the domains of science can be several. First of all, there's the macroscopic domain, which is shown in this big picture here. Now, what that means is a domain that can be detected by the senses. So this is what's known as the macroscopic domain, and the term macro means large, scopic means seen, and so this is a domain that can be seen without the aid of special equipment. The second is the microscopic domain. Now, the microscopic domain is not shown in this slide. That would be something that could be detected, but only detected with the assistance of some sort of device, such as a microscope. Micro meaning small, scopic meaning seen. And then there's something called the symbolic domain, and this is depicted here. This is, they've said in this slide that this B, they try to imply that this is the microscopic domain, but you can't see molecules under a microscope. You can only see much larger things. But these are actually two examples of what's known as symbolic domain. This means that you're using special symbols, in this case, the large balls and little balls, and also, or you're using letters to depict something in the macroscopic domain. So for example, up here is water as a gas form, and this is what it would look like symbolically with much space in between the molecules. And here's what it looks like with letters, with a little g meaning gas. Here's a block of ice, which is water in the solid form. And here it is linked together. The molecules are now linked together. And here it is H2O with an S, meaning solid. And then here it is in the liquid form. And here they are, they're not linked together, but they're closer together than the gas form. And so these are the three domains of science: the macroscopic domain, the microscopic domain, and the symbolic domain. This can also be shown as the phases of matter. There are three phases of matter shown here. The first phase is the solid phase, where the molecules are fixed in all three dimensions, the x, the y, and the z axis. Because of that, it has a fixed shape and a fixed volume, as shown here. Second is the liquid phase. The liquid phase is where the molecules are fixed in one dimension, so the volume is fixed, but the shape is not fixed. And so when you pour a liquid into a container, it assumes the shape of the container. And then lastly, you have the gas phase. In the gas phase, the molecules are not fixed directly to each other. Therefore, there is no fixed volume nor fixed shape. And it will assume the shape of whatever it's being held in. And you can see here that if you pulled that top off, then this gas would then escape, which won't happen with a liquid. Now, when we talk about materials, many times we talk about in terms of weight and mass. Now, it's very important to understand the difference between mass and weight. Mass is defined as the amount of material in an object. It's the number and size of the molecules that make up the object. The mass of an object does not change depending on where it is. For example, if an object has a certain mass on the Earth, it has the same mass on the Moon, has the same mass on Mars, has the same mass on Jupiter. Conversely, or separately, weight, on the other hand, is the force exerted by the mass, and that requires gravity. If you've had basic science, you might remember that force is equal to mass times acceleration. And when you're on a planet or in a particular environment, the acceleration is called gravity. And so the weight of an object is the force that's generated by that object, and this can change, and the weight of an object can change if the gravity changes. And so the weight of an object on the Earth is not the same as the weight of an object on the Moon, or the weight of an object on Mars, or the weight of an object on Jupiter. This is an important distinction to always keep in mind and make sure your conversation is accurate when you're talking about this. Now, as I said before, mass is always the same. Matter or mass cannot be created or destroyed. If the mass changes phases, none of the actual masses, it only changes from a liquid to a gas to a liquid, or a solid to a liquid. So that's what's meant by conservation of mass. Now, conservation of mass is an extremely important property that we will refer to again and again and again in chemistry. And it will be very important to keep this in mind when you do chemical calculations. And what's important here is, for example, you have pre-beer, and pre-beer is a combination of sugar and some other stuff in this top part. This ferments and becomes beer, which has carbonation and alcohol. Now, in the process, going from here to here, in that chemical reaction that occurs, no mass is lost. So if you have a kilogram of beer, which is a mass unit of beer on this side, you will have a kilogram of pre-beer here. Then you'll have a kilogram of beer on this side. Similarly, this shows the same thing in regards to a battery. A battery starts out with sheets of lead and lead oxide with sulfuric acid. Now, as a battery gets used, these react together and form lead sulfate and water. The mass on this side of this arrow is going to always be the same as the mass on this side of the arrow. And that's the concept of the conservation of mass. Now, substances are made up of atoms, and atoms put together form what are known as molecules. And so an atom is the smallest part of an element that has the properties of that element. And this is shown here on this side, right here. This is a block of gold, or a chunk of gold. Gold is made up of single individual atoms of gold. And there's nothing in here but gold atoms. And so that is an element. An element is made up of atoms and nothing else. A molecule, on the other hand, are two or more atoms which are joined together by a binding, which is a chemical bond. And actually, this is the same gold with the atoms being bound together. And you see that you can form little blocks inside here of gold, which represents several atoms bound together in an atom molecule. Now, this is probably not the best example of a molecule, because many molecules, much more molecules, are made up of different atoms. Here's an example of several different types of molecules. Now, remember, we said that these were individual atoms here and here, and here's the little white balls here are supposed to represent hydrogen atoms, and the little red balls represent oxygen atoms. And hydrogen atoms usually float around holding hands in pairs, and there's a bond there. So this is a hydrogen molecule represented with the letters H2. Here are oxygen molecules represented by the letter O2. Now, when phosphorus gets together, it binds together in either groups of 4 or actually groups of 10. And here you see a group of 4 phosphorus atoms together forming a phosphorus molecule. And here's a sulfur atom or molecule put together with 8 sulfur molecules, 8 sulfur atoms. I'm sorry, I misspoke. This is 1 sulfur molecule put together with 8 sulfur atoms. Then we have water, which is 1 oxygen atom and 2 hydrogen atoms. This is carbon dioxide, which is a common gas in the atmosphere. Here you have an oxygen and 2 carbons. And then lastly, here's glucose or sugar. There's 6 carbons 12 oxygens, and 6 glucoses, and that's represented right here. Now we're going to stop at this point, and you'll need to go on to section 2 to continue this lecture.